Hello, and welcome to the Aether community meeting. Thank you for joining us. Now I'd like to turn it over to Larry Peterson, who will provide some background about our session today. Larry?
Thanks, Denise. Good morning, everyone. We're going to hear about some research that Sundar and his colleagues at Stanford, Cornell, and Princeton have been doing recently in the context of Pronto. Just to set a little background, Pronto is a pretty substantial DARPA contract that's been running over the last 3 years that has used Aether as its underlying platform and helped to build out Aether. And we've had other talks here about the 5G aspects, about the edge cloud aspects of it. What we're going to hear about today is a little bit more on the underlying network infrastructure, and in particular, how to take advantage of programmable switches and P4 programmability in the switching substrate that underlies Aether, and then for which Pronto is the larger research project. So with that little bit of background, let me turn it over to Sundar and let him tell you about his work. Go ahead.
Okay, thanks, Larry. Can everyone hear me okay?
Yep.
Okay, sounds great. So hi, everyone. My name is Sundarajan. I am a PhD student at Stanford, advised by Nick McKeown, and I work closely with Professor Nate Foster at Cornell University. I'm excited to tell you about Hydra, which is a research project, as Larry mentioned, under the Pronto umbrella. And I'm also excited to tell you how we're using Aether as the underlying substrate to test out our research ideas. Okay, let me get started. So let me start by noting the research team. It's a big team spread across Stanford, Cornell, Princeton, and Intel, and ONF. So you see me on the top left, and then my advisors on the bottom right. So yeah, let's get right into it. So the observation is that networks are supposed to be simple, or at least historically speaking. So when you look at what a network does, it essentially takes packets, looks up the output port for a loose definition of output port, and sends the packet along its merry way. Okay, so this simple behavior. However, we see that the reality is getting more and more complex as we go. For instance, if you look at one single switch that is deployed in a traditional data center, it is composed of layers upon layers of hardware and software interacting with each other. For instance, this is a diagram from Google's data center deployment, and this is what one of the switches they use look like. So what is important is not the layers of complexity, but the fact that the complexity adds up to more 10 million lines of code. You could argue that a lot of it could be attributed to the switch Linux running on the switch, but even apart from that, there's a lot of complexity that is seemingly out of place in networks that are supposed to be simple. And this switch does not, and this does not even include the complexity that comes in from the control plane. And when you add that up, for instance, a typical control plane like ONOS, which is used in Aether, that brings with itself another million lines of code. Okay, so this idea of networks being simple is really not the case, and networks are more and more complicated as we go, right? So in the face of all this complexity, the question that we ask is, how do we build trustworthy networks, and how do we ensure that networks are behaving according to how we want them to behave? Right. So I will talk about a couple of approaches that people have used in the past, and then I'll talk about our approach and how that fits in to the rest of the literature. So before we talk about the approaches, let me use a very simple motivating example so that we can see how the approaches contrast from each other. So the motivating example is that there is a topology which consists of switches of two colors, red and blue. And the policy that we want the network to follow is that every packet should only traverse switches of a single color. What that means is that if a packet has traversed only red switches until this point, it should traverse, it should not go to a blue switch at any point in the future. And although this policy seems pretty simplistic, we see applications of it in SDN and other services provided by cloud providers, with some little more complexity added to this. So um, if you want to verify this policy, like how do we basically go about building trust that this policy is being adhered to? So the strawman approach is to basically offload the policy enforcement to the routing device vendors, and essentially what we're saying then is that you're trusting your Cisco or Juniper routers to implement the desired policy correctly. And we call this form of trust as axiomatic trust, and it's a strawman. And as you can see, it's somewhat it has worked in the past, but it's a little bit ridiculous. If something is security critical, offloading it to hardware does not seem like the best way to go, right? So in response to this, the community has recently invested in another approach, which works in the following way. It basically constructs a model of the network behavior, okay, and then it verifies assertions and checks the policy in this model of the network, okay. And if the assertion does not hold, then it can take corrective action. So what are the approaches I'm talking about in particular? I'm talking about header space analysis, Veriflow, Anteater, Batfish, Minesweeper. HSA came out of Stanford, and Batfish, Minesweeper are control plane verification software used by Microsoft, and also there's some startups using it. But the high level bit is that you create a model of the network and you check invariance in that model. Okay, so how can this go wrong, or are we done, right? Because and the reason we are asking this question is that this approach has seen a lot of success both in industry, academia, as well as startups. So where's the gap, right? So the gap is basically the following, that if you consider this Venn diagram and this larger circle as depicting all network behavior, then the model behavior by definition is only a subset of all network behavior, okay? So this raises a bunch of problems, right? There could be bugs in the unmodeled behavior. Secondly, the model may not even reflect reality. The operator might be making some simplifying assumptions while constructing the model, which may not reflect the ground reality. So those are more critical limitations. The softer limitations are that the model may be tedious to construct, as has been seen in academic literature, and model checking may not scale, right? So since we are verifying the entire network at the same time across all possible inputs, practitioners and academics have noticed that it's sometimes hard to scale model checking, right? So in the face of all these limitations is where we come in, and the question that we asked is that can we build a network that checks itself at the time of operation, right? So how would that look like? For inspiration, we look at parallel work in software engineering, in the software engineering community. It's called runtime verification. And let me briefly draw a sketch of what that looks like, and then we can see how we got inspired to apply runtime verification to networks, right? So in runtime verification, there's a system that we want to gain trust that it's operating correctly. So the way we do it is by wrapping the system with a monitor that includes two things. The first thing is just instrumentation or logging of what the system does. And this produces execution traces, okay? The second bit is that as the system is running, it checks predicates, which are typically safety properties. Details are not important, but yeah, basically it consumes execution traces and checks predicates as the system is running. And this provides the ability that if the predicate fails, then it can halt the system or prevent it from going into a bad state, right? So there is a lot of work. It's in this runtime verification field. It's a rich space. People have been working on this for a couple of decades at least, and some prominent examples are this eraser work, which is a way to detect data races at runtime, and more recently we've seen runtime verification make its way to the Linux kernel as well. Okay, so the question we ask is how do we get inspired by this? Can networks be repurposed to do runtime verification? And that raises a bunch of questions, right? So the first thing we want to do is, wrap the network around, wrap some instrumentation around the network. And sorry, yeah. So the question is, what would such instrumentation look like? What kind of execution traces can we use? What predicates can be done? And what does halting behavior look like, right? So these are a rich set of research questions which we had a lot of fun working around, and I'm happy to tell you more about our work. So before we go into our approach, let me draw a quick comparison to the limitations that I pointed out in analytic trust or model checking. So the first two issues are kind of addressed by the runtime verification because it verifies a running system, and by doing so, it sidesteps all the issues that the model could have, or the model of the network could have. For instance, there is no unmodeled behavior because we are working with ground reality. And since we're working with ground reality, the model by definition, there is no model, or if there is, it reflects the reality. So that's how RV or runtime verification addresses those issues. And for the second set of issues, RV is inherently more scalable than model checking because we are verifying only the inputs that we see in production or during the active deployment of the system. And we're not concerned with all possible inputs. So that makes RV slightly better in terms of scalability. Okay. So this is how we slot in. We call our approach synthetic trust, and it essentially says that we check every packet at runtime that if it corresponds to the desired policy. Okay. So now let's go back to our color isolation example and think about what such a synthetic approach would look like. Okay. So let's remind ourselves the policy is, packets traverse switches of the same color. And let us also make the observation that the policy should be enforced irrespective of how the network implements its forwarding, right? So for instance, the network could be implementing its forwarding using these functions phi, which depict what each router does. It could also be implementing forwarding using a different set of functions. And we want the same, policy enforcement mechanism to work irrespective of how the network does its forwarding, right? So in another way, basically the monitoring or enforcement is independent of how the policy is implemented by the network. Okay. So in this toy example, one way we could enforce this policy is by doing the following: is basically we capture the first hop's color on which the packet arrives and add it to the packet. Okay, so the red is added to the packet, and packet makes its way forward. The predicate, now we run predicates on basically the color that is captured on the packet and see if it matches the current switch's color. If so, we forward the packet, and at the last hop, the predicate would fail, and we drop the packet, right? So for this toy example, tracing the previous hop's color or the list of switches color on the packet would, and running predicates on every switch would essentially be sufficient to enforce this policy. Okay, and now basically what we see is that even this toy example gives us important hints for what runtime verification should look like. For instance, we note that we should carry network-wide execution traces on packets. We need the ability to evaluate predicates per packet, which is super fine-grained, and need to operate at data plane timescales. Okay. Thirdly, if a check fails, then we need the ability to stop the packet from making forward progress. Okay. And the last requirement for runtime verification is, as I mentioned earlier, the monitoring and forwarding should be independent. Okay. Any questions until now? Okay, I'll just keep going. So how do we take these hints for runtime network verification and realize this in today's networks, right? So one approach would be to use P4. Okay, so what does P4 provide us? P4 basically provides us the ability to tell the router how to process packets, right? And how could we use P4 to implement monitoring? We basically take the forwarding code, or the P4 program that implements the forwarding, and we add the 3 bits that we care about and construct a new P4 program which composed of the forwarding as well as the tracing, predicate evaluation, and halting. And this becomes one big P4 program, and we could potentially write the monitoring code directly in P4 and be done with it, right? And that might be good enough for many use cases, but our argument is that while P4 brings us a lot of benefits, it's a stop short of other important benefits that is required for network-wide policy enforcement. So let's look into that first. So P4 provides us the ability to evaluate predicates on a per packet basis. It also provides us halting behavior. We can drop a packet or report it to the control plane. What it does not provide us is a neat way to collect network-wide execution traces without worrying about where a packet is in the network, what else is happening in the packet tracing. So because and the reason this limitation exists is because P4 only provides a single switch abstraction, whereas we want to enforce network-wide policies, which involves collecting network-wide execution traces. Okay, so that's the first limitation of P4. The second limitation is that if both the forwarding and monitoring is implemented in P4, it's harder to enforce independence. And what that means is that the same bug that is plaguing the forwarding behavior could also be present in the monitoring behavior, which kind of goes against all the benefits that monitoring should bring. So in the face of these two limitations of P4, we basically designed a new DSL called Indus. And okay, before I talk about that, our system to do runtime verification is called Hydra. Okay, and as part of Hydra, we designed Indus, a new DSL, to capture network-wide predicates and network-wide traces. Okay, so I provided an example, Indus program for our toy example, and let me go over this step by step so that you can build intuition for what the Indus language provides and how it can be used. Okay, so in this program, you see different kind of variables declared at the top, and you see 3 kind of code blocks: init, telemetry, and checker. Okay, so the 2 types of variables that you see here are tele and control. Tele variables are carried on the packet as the packet makes its way through, and control variables are provided by the control plane that the packet has access to at runtime. Okay. Now, what the 3 code blocks are doing is essentially what you saw earlier in the visualization, but I'll go over it for building intuition. So the init code block executes at the very first hop that the packet hits in the network, and it keeps track of the first hop's color. Okay, and the first hop's color is derived from this control variable switch color that is available at every switch in the network. Okay, so we keep track of the first hop color. We carry it on the packet since it's a telemetry variable, and then we keep track of a list of hop colors, which we basically keep appending to at all the subsequent hops, and the telemetry block basically captures that. So this executes at every hop, and it keeps track of all the hop colors seen by the packet as it traverses the switches. And the checker code block is the last one. And this is the one that enforces the predicate. It executes at the last hop, and it basically checks if each hop that the packet traversed has the same color as the first hop. And if not, we have this reject primitive, which is essentially equivalent to a drop. And we make sure that the packet does not make forward progress. Okay. yeah, so I talked about two kinds of state, packet variables and control variables. And yeah, so the initialization happens at the first hop. Telemetry happens at every hop, and it can only, it has this append only, a trace that it cannot, modify previous aspects of. And this trace is carried on the packet, and a checker runs at the last hop before the packet exits the network, and implements the predicate. Okay. And packets that fail check can be dropped or reported to the control plane. So note that one big assumption in this program is that we have a one big switch model for the network, where you can think of the network as a single big switch. So end to end, we will prevent bad things from happening, but in between the network, potentially bad things could happen. For instance, because the checker runs at the last hop, we could potentially have packets traversing a mixture of switch colors, but before that packet exits the network, we will basically know that it had violated the predicate in the past, and we would make sure that it does not exit the network, which satisfies the one big switch assumption that this approach is working with. So here's another example of a property that you could verify in Indus, our programming language. So we could verify, load balance, where the invariant, simply put, is that the load is equally balanced across two output ports on every switch in a packet's path. And here's the Indus program to do that. So I will not go into the details, but I will talk about, a different kind of state that our language provides, and those are called sensors. So we noted telemetry state, and we noted control plane state. Sensor state is essentially state that is kept track of across packets. You could think of as registers, if you're familiar with P4, or counters, and that's how they're implemented. But from Indus's point of view, you have access to these variables across packets, and basically that's central to enforcing this load balancing property, which says that two ports should be equally utilized across multiple packets. Okay. The semantics is that the central variables reside on switches themselves, not on packets. And for this particular property, we essentially update the sensor variables on every switch and carry the values seen seen of those sensors when the packet traversed them as telemetry variables, which are then verified by the predicate at the end. Okay. So yeah, I think those are the important bits. Yeah, we have more control variables to figure out, which port is, the left port and which port is the right port, and so on. And note that this, even though this program seems simplistic, even though it verifies, balance across two ports, you could see that how this program could be simply augmented to keep track of, load balance across several ports. Okay. And yeah, those are the important bits, at least for this program, and noting that we have sensor variables also as part of the language. Okay. Now we had a couple of research questions to answer in terms of why we designed this new language. The first one is is the language powerful enough to express rich network-wide properties? And we prove that the language can encode any network-wide property written in LTL, linear temporal logic. So this is a kind of logic used heavily in runtime verification literature. And we essentially show, the proof is not part of this talk, but we essentially show that any property that you could write in Indus, you could reduce to a logic formulae that you could write in LTL. And LTL has seen a lot of adoption and usage across the RV use. The second research question is, how do we, now that we have written a program in Indus, how do we convert it into an efficient representation that can run on modern networking hardware? So for this, we essentially built a compiler that takes Indus programs and spits out P4 code for every networking device in the network. And it combines the monitoring P4 code and the forwarding P4 code into a single binary. and ensures that the forwarding and verification happens at the same time. Okay. So now I'll talk about some runtime case studies of Hydra and how we ended up using Aether as part of our research. So we developed some properties that capture key invariants for Aether, which you're familiar with, and this is the topology. The properties that we used are some simple ones like loop avoidance, leaf spine routing, and some other simple ones. We wrote Indus programs for all these properties, and we combined them, and we turned them into one big Indus program which verifies all these properties. And we deployed, compiled and deployed the checkers in Aether's dogfooding testbed at Princeton. Okay, and we injected faults which violate those properties in terms of buggy forwarding rules. And we see on in the time series graph on the right that as soon as the fault is injected, the packets are start getting dropped and getting reported to the control plane. And then as soon as the buggy rule is removed, we see that the network traffic goes back up to where it was previously. And the point of this slide is to just show that it works, and we have a runtime deployment. And now I'll talk about the application filtering policy in Aether, which we ended up finding or refinding a known bug with. Okay, so here's the topology again, but augmented with the SDN controller, 5G mobile core, and the ROC on the top. Okay, the particular aspect of Aether that we wanted to verify is called application filtering, which states as an invariant that only designated 5G UEs should talk to designated edge applications running on servers, which identified by IP address, IP protocol, and layer 4 port. Okay. For instance, if a 5G client is not allowed to talk to the internet or a particular edge application, application filtering is the way that feature or functionality would be implemented. Okay. So in terms of the telemetry that we used for verifying application filtering, we basically carried the UE and application identifiers, as well as the filtering action, which gets looked up as a control variable. Okay. And the predicate that we check is of two kinds. If the packet was supposed to be dropped according to the control rules, but got forwarded due to some error in the forwarding fabric, then we basically drop the packet and send the report. Okay, make sure it does not make forward progress. And if the packet was supposed to be forwarded but got dropped, we just send a report because we have already lost the packet. So having said that, like what you see on the left right now is the Indus program for application filtering. It seems complicated, but really it's super simple. And what it's doing is, at a high level, in the init block, it first figures out if a packet is an uplink packet or a downlink packet. And based on that, it fetches the UE and application identifiers from the appropriate locations on the packet. For instance, if it's an uplink packet, it means that it's GTP encapsulated. So the UE and application information would be in the inner IPv4 headers. And if it's a downlink packet, it means that it is not encapsulated yet. And the UE and application identifiers can be fetched from the outer IPv4 or the only IPv4 header in the packet. Okay, so after having fetched these identifiers, it basically looks up this filtering action from the filtering actions control variable provided by Indus, okay, by the Indus control plane. And apart from that, there's no other telemetry that's carried. So that's why the telemetry block is empty. And the checker, as I mentioned earlier, verifies enforces two kinds of predicates. If the filtering action is 1, which means the packet should have been dropped, but has not been dropped yet, it basically stops it from making forward progress and sends a report with the corresponding identification information. And similarly, if the packet was supposed to be forwarded but got dropped, okay. So this is the Indus program. When we ran this in the Aether testbed, we were able to confirm a known bug in application filtering, which can be seen on the right. So basically, the bug comes from the fact that application filtering is implemented using multiple tables in Aether for optimization reasons. And what ends up happening is that table rules are used for the same application filtering policy. The table rules are used across. Actually, let me take that back. For multiple application policies, the same table rules could be used in different combinations, which means that what we essentially saw is that by slightly playing around with the priorities in terms of the rules that get installed, we can basically make a packet follow an application filtering rule that it should not have followed. And this was, a known problem in Aether, and we were able to confirm that using the compiled P4 code and that is produced by the Indus compiler. I could go into more details if you'd like, but at a high level, it comes from the fact that rules across tables are used across different application filtering policies, and that's where the bug comes from. Okay, I see a question. So the question is, what would be the impact of filtering on the QoS performance, congestion, security concerns, and packet drops? Okay, that involves a lot of things. So basically, in terms of performance, at least the data plane performance, I will show later on that we don't add any overheads because we're using Tofino switches, and if the program fits in the Tofino, it runs at line rate, so there's no QoS related concerns. In terms of congestion, I don't see how filtering should impact congestion, but maybe you could tell me more. And similar for security concerns.
So I may be reading too much into this, but I'm wondering if the question is about policy, establishing properties and policies that are representative of some behavior that's congestion related.
I see. Yeah, so those kind of policies are the most interesting ones. For instance, the load balancing was essentially a QoS policy that we could check. For a general policy, if the question is how could we implement that in Indus, is that the question?
Let's assume it is. It's hard to be super interactive with the typed in, but go ahead. I think that's reasonable.
Yeah, so I think those policies. Okay, so those policies are more complicated to specify, but also the more interesting ones. So from an Indus point of view, you could implement checkers for those policies, but what we have seen in experience is that compiling these programs into Tofino can be sometimes challenging because the resources are quite limited. So yeah, basically we might have to do some work to optimize the compiler for more complicated policy. But in terms of the bare bones, the telemetry variables, the sensor variables, and the control variables provide all the context that is needed to verify QoS policies, congestions, and other security related policies. So
I was going to hold a question at the end, but this kind of triggers it. So let's go ahead and have the discussion now. It's related to this, which is, I guess it's an overhead question, which is not latency, but table, how much table space you have. So there's a certain complexity to these properties that indirectly then impacts how much of this very scarce resource you'd end up using. And so I would suspect that, and it's kind of related to this question, there's a certain class of properties that work well, are efficiently represented in this, and some that maybe aren't. Do you have any experience, or if you're going to get to this later than that, we can postpone it, but kind of experience as to what type would be most appropriate?
Yeah, I think the policies that are most appropriate are the single packet properties. Those are, single packet properties could still use, state available only on the data plane. But those are, the most natural fit. When we talk about multiple packet properties, at least the work as it stands until now, it uses sensors which on Tofino switches, which basically have a lot of limitations. You can only access them once for a packet, which means that you might have to spread your policy enforcement across multiple sensors, which introduces dependencies and reduces the likelihood of program fitting. So short answer to your question is single packet properties, but a lot more longer term answer is that we're seeing a lot of programmability move into the NICs and away from the core of the network, as we saw from Intel standing back its Tofino support, well, not the support, but at least development. And what that means is that for a NIC, you have essentially 10 to 100 times the resources as compared to a switch, which means that more complicated properties are a more natural fit on NICs. So if the fabric could provide telemetry with, like INT telemetry that is, pre-programmed, you could still run complicated predicates at the edge where you won't have as much of a fitting concern as much as.
Yeah, that's a great answer. Right, the potential is pretty substantial there. So let's go ahead and continue on. Okay,
yeah, sounds good. Thanks for the question. Yeah, so let me talk about overheads really quickly. So these are preliminary numbers, and we're working on them as we speak. So I'll talk about latency first, and what we want to see is that the RTT of packets that are traversing the network fabric with and without Hydra checkers. So I basically took the 5 properties that I described 2 slides earlier, and that's the line in blue. When all those 5 properties are enforced together, we see this RTT graph over 30 minutes. And when we have no verification running, we see this RTT graph in orange. And for all practical purposes, it's overlaid on top of each other. And we also run a statistical significance test on the probability distribution, and we saw that the baseline forwarding program and the forwarding program with 5 properties being verified have the same RTT for without any statistical significance. So yeah, in that sense, at least in terms of latency, the overhead is negligible, and this kind of makes sense because if a property or if a P4 program fits on a Tofino switch, it is guaranteed to run at line rate. Now you could still have some amount of latency addition in nanoseconds at least, but we don't see it in terms of the RTT numbers, which operate on millisecond or even microsecond timescales. Okay, so that's latency. Let me talk about Tofino resource utilization really quick. And before that, I should give an overview of the resources that matter in a programmable switching pipeline from Hydra's point of view. So here's what a programmable switching pipeline looks like. You all must be familiar with this, but just for the sake of completeness, there's a programmable parser which takes bits from the wire and places them on these structures, which are called which are held in the packet header vector. The PHV is essentially a bus which makes its way across the pipeline stages provided by the switching pipeline. There could be multiple pipeline stages, and this bus could be modified as the packet makes its way through. And at the end of the pipeline, there's a deparser which takes the structure and produces bits that go back on the wire. Okay, I'll get to this question in a minute. Yeah, so the overheads that are important from Hydra's point of view are the pipeline stage usage, because that controls if a program will fit on a Tofino. The second one is PHV usage, because PHV is a very scarce commodity on switching fabrics. And third one, which we looked at, are TCAMs used in the programmable parser, and that is important because we are adding fields and parsing to the packet in terms of the telemetry variables. So we want to see if we are not using too many TCAMs in the programmable parser. So okay, so here's the first bit of the graph, which shows stages and normalized to one here, but like essentially the Ether's P4 program is using up all stages on Tupino. Okay. And we see the PHP usage and parser TCAM usage as a fraction. Okay. Now I augmented the graph to essentially take the baseline program and add to it a property of interest. For example, the IPv4 routing, ECMP, load balance, port validity, VLAN isolation, and loop avoidance. And what we essentially see is that the number of stages that is taken by the combined forwarding and verification program is the same, despite more resource usage on the existing stages. So this shows that in a lot of cases, the forwarding and verification can be placed in parallel to each other on the switching pipeline. Okay, so that's good. And we also see that the PHP parser TCAM overheads exist, but they're not, out of the park. So in for these, simple properties, I would like to say simple because these are still, single packet properties, except for the ECMP load balance. The overheads seem to be negligible, or at least manageable. And the more general answer to the overhead question is that there's no free lunch. So if you want to do verification, there will be some overhead. But hopefully using these graphs, I've shown that the overhead may not be as much as you think. And this is especially considering that the verification is running at line rate per packet. So wherever it makes sense in terms of a property that is so security critical that not even a single packet should violate it, even there the overheads may not be as much as you think. Okay. So yeah, now I'll get to the question. So the question is, what is the test bed setup for experiments? Is it simulation or the real test bed? So the answer is it's the real Ether test bed, which is shown. Yeah, which is shown here. So this is the Ether test bed which we run our experiments on, which means our verification is running on hardware switches, along with everything else enabled, ONOS, the mobile core, the ROC, and all that. And we found that the policy violation bug in real hardware. So yeah, all of this is on real hardware, and we are it's a 2x2 fabric connected by edge servers, and yeah, a 5G base station and mobile clients. So yeah, there's that. So I was done talking. Okay, so another question is, are these devices in the same building? The answer is yes. So these their switches are part of a rack. The servers are part of a rack, and the switches are right next to them, and the mobile devices were in the same building or room as the 5G base station, which was in the same room as the switches. Okay, so another question is code available or will it be available? So yes, we will make the code available. So right now, this work is part of an active paper submission. So once we hear back on that, we expect to make the code as well as instructions on using it publicly available. Okay, so let me jump to the conclusion. Yeah, okay, before that, there's a bunch of future work which we're really excited about. So right now, as you saw, we were using programmable switches in the fabric to provide telemetry, but you could also imagine fixed function switches providing, predetermined telemetry and checking predicates at the edge on the NIC, or even in the kernel using eBPF or similar technologies. So that's one. So that's super exciting. And the closer we go to an end host, the more richer context we have about packets. So that allows us to do more complicated telemetry and verification, as opposed to this per packet behavior, where a lot of context about what the packet is lost in the fabric of the network. So that's one. The second thing is the ability to root cause packets that fail checks, as opposed to simply halting their progress. And if you're able to root cause packets, then we'll be able to do closed loop control in the sense that we could actuate the network back to a known good state based on the class of packets that are failing checks. So that's super interesting and in line with the original goal of Pronto. The last two are more forward-looking, and they are basically, we could do for probabilistic verification, where instead of verifying checks on every packet and accumulating the corresponding telemetry overhead, we could check 1 in 1,000 packets, or check them probabilistically, in line with some work we've seen in the context of INT. It's called probabilistic INT, where we essentially, the idea is to reuse the telemetry across multiple packets instead of adding it to every packet. And the last one is potentially also very interesting, where the ability to verify higher level service abstractions, for example, Kubernetes level like service mesh networking, and those kind of things could be composed of per packet checks. And we believe that the Indus language provides a lot of the building blocks that one might need for verifying higher level abstractions, but the actual usage or like finding a killer application is ongoing work. Okay, so this is future work we're excited about. And in summary, I would like to note that networks provide telemetry for free. So our approach essentially takes this telemetry which networks provide, and networks can be augmented to provide, and wraps the network in a runtime monitor. And this is an underexplored approach to verification, and this kind of closes the loop between the axiomatic approach, where the vendor is doing all the checks, and the formal verification approach, where you model the entire network and abstract it away. So we believe that this underexplored approach bridges the gap. Okay, and in terms of contributions, we have a DSL called Indus, a compiler to turn Indus programs into P4 code. And the preliminary overheads seem manageable, but that is a story that's still in progress. So yeah, thank you for your attendance and your questions. Happy to take more questions and yeah, open it up to discussion.
So thanks. That's a great talk, and we'll give folks a chance to type in any other questions they have. But let me kick it off with a couple. So you touched on apps here. You used the phrase killer app, I think, maybe in your last slide. Could you give us a sense of where you see some real promising applications that you're aware of?
Yeah, so I think the killer apps is the thing that okay. So
we'll get back to those.
Yeah. Yeah. So the killer apps is the question that we are also exploring as we speak. So in our conversation with Aether, or the ST Fabric team in Aether, we found that application filtering was one potential killer app. The other one was QoS verification, as someone asked. That could be one, but we haven't written an Indus program for that. More generally, I think source routing could be a potential killer app, or verified network updates, wherein the network moves from one state to another due to some software update, and you would want an independent verification mechanism to be working around the clock to ensure that no invariants are violated in transition. So those are some things which we think are killer apps, but really we would also like the community to chip in and say that if you had the ability to verify properties on a per packet basis, what are some properties that kind of keep you up at night? I would love to hear that from.
Yeah, that would be great feedback.
Yeah.
So one of the next questions that from the audience has to do with, so you've tested this in basically a switching fabric in an edge. It's not a data center, it's an edge clustered switching fabric. If you were to go across a WAN with higher latencies, do you see how anything would change here?
So the quick answer would be if the combined, forwarding and verification program compiles on the switching fabric, then the latency impact should be minimal. But I think with fixed length pipelines, that question is not a given. Like the answer is not a yes. So yeah, there might be some work. We believe there's a lot of work in an optimizing compiler, which basically takes into account the switching fabric that's being compiled for, and reorganizes the program so that it takes minimal resources on the pipeline.
So just for clarity, which is kind of related to one of the other questions, you're outputting P4 code, and so it runs anywhere that P4 can be translated, correct?
That is correct. And so another way to answer that question is we could incorporate other backends, like eBPF or other whatever runs on the Pensando or other SmartNICs. So P4 is one backend we consider. We could have other backends. So whatever those support, you could run there.
Yeah, it'll be interesting to see. P4 seems to be getting pretty good traction as the shared expressive language translated to various backends. Hopefully that makes everyone else's life simpler. So I really like the way you talked about separating monitoring from forwarding, and bug introduced in one could carry over to the other. So effectively what that means is that you're depending on the Indus compiler to generate correct code. Knowing who one of your advisors is, can you talk about what assurances you can give me that your compiler is correct?
Yeah, so the first way to address the question is that essentially we're still producing P4 code, but we're reducing the trusted computing base to all of the forwarding to just this verification compiler. Okay, so we're reducing the trusted computing base, and this verifying the verifier question has been asked a lot in the verification community. And we could basically, since the programming model is so simple, we could make sure that the compiler, as it steps through its different passes, does not violate the semantics that is expected from the programming model. That being said, we haven't done any work yet, but it's in line for future work.
Yeah, good. Thanks. So you one of your slides earlier that showed the switching, the four switch switching fabric and the stack that sits above it, and the rest of Aether and the rock you mentioned, and so on. I'm just curious. It's clear the touch point inside of the switches. Could you just talk a little bit about what touch points, where the intersections are with the rest of the stack, ONOS, rock, and so on?
Yeah, that's a great question. So yeah, so the first touch point that you could think of is these control variables that are provided at runtime. Those are essentially implemented using tables, which means that you need a parallel control plane that is running as in tandem with the forwarding control plane. So we used ONOS, and it's like application framework to essentially specify the control plane as another ONOS app. But in the future, potentially you could imagine that if you want to remove that dependency also, if for example the ONOS or like the controller is likely to be buggy, you could basically have a different controller, from scratch, installing all the rules in data plane.
I'm going to guess you didn't have any touch points within the rock.
Yeah, touch points.
Okay.
So the only touch point from the rock was basically the application filtering policy, which is specified at the level of the rock, and that gets shipped to our ONOS app, which then translates it into rules for this.
All right. So in principle, at least, and it sounds like you did this, the ultimate control interface that an operator would do would be this, inject the property they want enforced, and then it gets handed down to the app. Yeah, good.
Yep.
So I don't have any other questions, and we don't seem. I'm saying, wait, maybe I need to scroll here. Nope, I think that's it. And we're pretty close to the top of the hour. So thank you very much for your presentation, and looking forward to following the work as you continue.
Thank you so much for attendance, and yeah, thanks for the opportunity.
Yeah, great. Thank you. Thanks, everybody.